Hi, my name is Lakshya Jain and this is my video for solution of maths in semester exam, question number 5. So let's commence. So the question is that we need to prove the identity that Laplacian of any function of derivative of any function f is s product of s into Laplacian of the function y minus f at 0. So before starting, I'm gonna go through over what exactly is Laplacian. So basically, Laplacian of any function f is integral with limit 0 to infinity e raised to power minus st into ft dt. So this is the basic definition of Laplacian that we have here. Now in this definition, s is actually a complex number, a complex variable, I must say, and t is also variable and it has a value greater than or equal to 0, and ft, the function ft, is piecewise continuous. So this is the basic definition that we have for Laplacian. Now we need to prove this identity. So Laplacian of f derivative can be written as 0 to infinity e raised to power minus st f derivative t. Now obviously if I need to prove this identity, so in this identity to be true, the Laplacian of f should exist, right? So in order to solve this, I'm going to first name an integral I, which is actually an indefinite integral. So I'm going to first calculate this or further explore this integral first by using the indefinite integral, and then I'm going to apply the limits to solve and to get our Laplacian of f derivative. So I'm going to name I as an indefinite integral, where I'm going to define I as integral e raised to power minus st ft dt. So I'm gonna further explore this integral, solve this integral by using integration by parts. I'm gonna name this as my first function e raised to power minus st, and I'm gonna name ft as my second function. So let's, according to integration by parts, let the first function remain as it is. The integration of this, this is the derivative here, e raised to power minus st f derivative t. So e raised to power minus st integral of f derivative t dt minus integral the derivative of the first function that we have, e raised to power minus st, multiplied by the integral of the second function that we have, f derivative t, and dt is here and this one is dt. So I'm gonna solve this. Now e raised to minus st. Now integral of f derivative t is nothing but ft minus, now derivative of e raised to power minus st is minus s e raised to power minus st. So this gives us minus s this is integral minus s e raised to the power minus st, and the integral of f derivative t is ft, this is dt. So this can be written as e raised to power minus st ft plus minus minus gets plus, e raised to power minus st ft dt. Now this was our indefinite integral. Now I'm going to put the limits that are from 0 to infinity. So when I put the limits from 0 to infinity, it basically gives us the Laplacian of f derivative. right? So if when I'm putting the limits in I get e raised to power minus st ft. The limits are from 0 to infinity plus s limit 0 to infinity e raised to power minus st ft dt. Now carefully examine this integral. Integral 0 to infinity e raised to power minus st ft dt. This is nothing but a Laplacian of the function f itself. We can see this in the definition. This 0 to infinity e raised to power minus st ft dt, integral of this. So this is same as the Laplacian of f, and in this I get limit t tends to infinity e raised to power minus st ft minus when I put 0, it gives me f of 0, because e raised to power 0 yields us 1. So and ft and f0, and this is nothing but Laplacian of f derivative. Now I'm going to hold this integral, hold this Laplacian of f derivative here, because I need to find or figure out the value of this term. So let's look into it now. So the term whose value we need to find for the moment right now is limit t tends to infinity e raised to power minus st ft. Now we know that for this identity to be possible, Laplacian of f must exist, right? So if Laplacian of f has to exist, it must have a finite value, right? So in other words, the Laplacian of f should be finite and should exist. So basically Laplacian of f, that is written as limit 0 from integral 0 to infinity e raised to power minus st ft, this must be finite, or in other words this should have a value that is less than infinity. That means it must be finite, right? And we know that if an integral must be if an integral of a function, let's name it ht, whose limits are from 0 to infinity, is finite, then limit t tends to infinity h of t has to be 0. If there is an function whose integral has limit 0 to infinity, and that integral must have a finite value, then that function whose integral we are doing at infinity, it assumes it has the value 0. So basically, since this integral exists, the Laplacian exists, therefore e raised to power minus st ft, when limit t tends to infinity e raised to power minus st ft is there, it has to be 0, right? So I'm going to go back to the equation that we had, that I had left, the Laplacian of f derivative. So this term now becomes 0. So I'm going to substitute it in the value in this equation. This yields us basically then Laplacian of f derivative is 0 minus the value of the function f at 0 plus s times the Laplacian of f, and this basically gives us that Laplacian of f derivative is nothing but the product of s into Laplacian of f minus f of 0. This is what we needed to prove, and hence proof.